Now we want to talk about the advanced version of the Solow model, which is with population growth and the technological growth. So given that it has the population growth, we assume the population growth rate equals n. When we say there is a technological growth, we assume the growth rate equals g, and this technological growth is associated with a particular type of the growth, which is called the labor augmenting technological growth, which tell us that when there is a technological growth, it increased the productivity of the labor. So then this growth augmented the production efficiency of the workers. So then based on that, we know for an economy that it has the population growth, then it tells us that the population at time t in fact equals 1 plus n to the power of t multiplied by L naught. When the economy is with a technological growth, we define a variable which is called ET, then this variable will grow at the rate of g. Given that this variable represents how does the technology evolves over time, and given that it is growing at the rate of the g, so we say that the ET equals 1 plus g to the power of t multiplied by E naught. So then you need to keep in mind that under this Solow model, we have the population growth and the technological growth. The population growth at the rate of n and the technology growth at the rate of the g. In here, let me illustrate to make sure that you guys understand what does this equation mean. So for example, if the technological level at the period 0 is E naught, given that the technological growth rate is g, so then we know E1 and it equals 1 plus g multiplied by E naught. So then what should be the technological level at the second period? It turned out to be 1 plus g multiplied by E1. So then it equals 1 plus g multiplied by 1 plus g multiplied by E naught, because E1 equals 1 plus g multiplied by E naught. So then we are going to have the second period's technological level equals 1 plus g to the power of 2 multiplied by E naught. And that is why when we set up the equation characterize the level of the technology and population at time t, we say that the population time t equals 1 plus n power to the t multiplied by L naught, and the technology at time t is equaling 1 plus g to the power of t multiplied by E naught. So similar to our practice for the Solow model, we need to define the economy, given that this is also a Solow model but with population growth and the technological growth, so that it means that all the assumptions we have for the Solow model remain the same. In addition to that, we adding the technological growth into the model. So what we want to do is that we need to first define the economy. We say that the economy has household. The household make decision about how much they want to consume. It turned out to be a portion of the income. The second equation that we want to have to characterize this economy is that the firm adopts a production technology by putting the capital and labor into the production process. In here, I do not write it out explicitly because we want to define a different version of the production function later on. So now let's keep it just as the output is a function of the K and L, which is the same as before. So then we also have the third equation characterize how does the capital evolve over time. We say that the KT plus 1 equals 1 minus delta KT plus the IT. K is the capital stock, delta is the depreciation rate, and I is the investment. Finally, we define the equilibrium condition of this economy, which tell us whatever amounts of the output need to be either consumed or invested. So later on, in order to reduce the number of equations, we will combine equation 1 and 4 and then introduce a new version of the equilibrium condition. So now let's take a look at these 4 equations in detail again. So what we have in here is that we combine the first and the fourth equation. From the first equation, we know consumption is the output minus a fixed portion of the output, and then the fourth equation tells us whatever amount that is produced need to be either consumed or invested. Therefore, if we combine these two equations, we are going to get the equilibrium condition for this economy. That is, then we will be able to, once we combine this equation, we are going to have an equilibrium condition that combines two equations under the model. We have the investment equals the savings. Then let's take a look at the second equation. We said that the output is a function of the capital and labor. Now we define explicitly, we say it equals A multiplied by KT theta, and then to a bracket that is ET/LT to the power of 1 minus theta. You may ask, what does it mean? Well, the A in here is the production efficiency we have been talking about. The K is the capital stock. The theta is the capital share. So then the 1 minus theta is the labor share. But now in here, we introduce a new term that is E, which is the labor augmenting productivity growth. And then the LT is the number of the labor that we put into the production process. So then why we want to, so then in here, we introduce a new version of the production function, which looks very similar to the Cobb-Douglas production function, but it preserves the property that when there is a technological growth, it augmenting the production efficiency of the worker, not the entire production process. So we call this the labor augmenting production technology. And then in this Solow model with population growth and the technological growth, we want to focus on this particular type of the production technology. And the reason why we do that is in fact for computation purposes, but it also consistent with the fact that we observe. That is, when there is technological growth, it somehow can improve the production efficiency of the workers. So then we want to focus on this particular type of the technological growth. Finally, the third equation is the law of motion. We know that under the Solow model, the law of motion is the only equation that characterizes how does a variable evolve over time. We have KT plus 1 and KT. And so when we want to look at the steady state of the economy, we need to focus on this particular equation. So now we want to move on to talk about how to solve the Solow model under this new setup. So as you can see from here, that if we look at the aggregated variables, the system of equation we set up look very similar to what we had before. The only difference is that we introduce a new form of the production technology, which is the labor augmenting production technology. And then we can introduce the technological growth into the model. So now let's take a look at how to solve this new version of the model. Here we want to first introduce a concept called the per effective worker. That is, we want to define a new variable that is in lowercase, which equals to the aggregated variable divided by the level of the technology and the population. If you may recall from what we learned before, we defined the lowercase variable to be the aggregated variable divided by the population size. The reason why we want to do that is that we want to take the action called the trend, because once given that for this economy, we have the population growth and the technological growth. If we take out the growth of the population and the technology, then we can focus on the variable that no longer have growth. That is because the technological growth and the population growth are the only growth of this economy. If we take out the growth trend of these two, then the economy will degenerate it into the model very similar to our previous analysis. That is when it is at a steady state, even though it is a broadly defined steady state because the variables still grow. But then if we look at the lowercase variable, then once the economy is at a steady state, then it will have the same value. This practice will make our analysis easier because once we take out the growth trend, then we know that for the lowercase variable, if the economy is at a steady state, it will stay the same. So after we define the new variable called per effective worker or labor, then it will make our life easier for the analysis because now after we take out all the growth trend, then once we look at the lowercase variable, then the steady state of this model expressed in the lowercase variable is as if the economy at a steady state, all the variables value need to be the same, and it makes the computation much easier. So then we need to do something called the trend, and we introduce a term that is called per effective labor. So because we define the variable in this way, so then we define the lowercase ct to be the uppercase ct divided by the ET and LT. We apply the same practice for output, investment, and the capital stock. So then now let's take a look at the equations. Once we define these new variables, how will that affect the system of equation? Well, we know the system of equation need to hold. Therefore, when we look at the first equation, we say when we express it in terms of the aggregate, the CT is equal 1 minus S multiplied by YT. So then if we want to convert this equation into the lowercase, then we can divide both sides of the equation by ET and LT, and then we are going to have the first equation converted into the expression in the lowercase, which is the consumption per effective of labor equal to 1 minus S multiplied by the output per effective labor, keeping the equation hold. And so we have a new version of the first equation expressed in the lowercase. We also do the same thing for the second equation, which is on the production function. We know that if we want to convert the expression from uppercase to lowercase, we divide both sides of the equation by ET and LT. And then for the left-hand side, we know it will equal the lowercase YT. But then for the right-hand side, what we know is that the denominator ET and LT can be expressed as ET-LT to the power of theta multiplied by the ET-LT to the power of 1 minus theta. And then the first part can go together with the KT, and then we can successfully convert the uppercase KT into the lowercase kt. Then the second part, ET-LT to the power of 1 minus theta, then got cancelled out. So then we are going to have the second equation that successfully converted into the lowercase. Now let's take a look at the fourth equation. Again, we divide both sides of the equation by ET-LT. Then we can convert the equilibrium condition into the lowercase yt equals ct plus it. So then we know when we want to draw the Solow diagram, we can combine the first and the fourth equation together. We are going to have the it equal s multiplied by yt. So then, of course, we can either combine the 1 plum with the 4 plum, or we can just simply determine this equation, and then we are going to have the lowercase it equal s lowercase yt. Now let's take a look at the law of motion and to examine how to convert the expression from the aggregate into the per effective worker. So then in here you will say, given that the right hand side is denoted at time t and the left hand side is denoted at time t plus 1, given there are two variables on the right hand side and only one variable on the left hand side, so then to do the deterrent that we can divide both sides of the equation by ET and LT. Then we can successfully convert the right hand side into 1 minus delta lowercase kt plus the lowercase it. But then how about the left hand side? We know that the kt plus 1 over ET LT does not equal kt plus 1 in the lowercase. But then what we know is that the lowercase kt plus 1 equal the aggregated t plus 1 divided by the ET plus 1 and LT plus 1. Given that the KT plus 1 and ET, LT are not the right couple, we just separate it out. And then we divide it by a term that is KT plus 1 and LT plus 1 below the KT plus 1. And then given that we want to keep the equation hold, so then we need to multiply it by the ET plus 1 and LT plus 1 again. So then what is et plus 1 over et? It is exactly equals 1 plus g. What is lt plus 1 over lt? It equals 1 plus n. So then in other words, now the left-hand side can be converted into 1 plus g, 1 plus n, multiply lowercase kt plus 1. So then we have the new version of the law of motion expressed in terms of the per effective worker, which is 1 plus g, 1 plus n multiplied by kt plus 1 in lowercase equal to 1 minus delta kt plus the it. So then what we have in here is that we successfully converted the law of motion expressed in the aggregated variable into the variable that expressed in terms of the per effective worker. So then before we move on to look at the steady state condition of this model, we want to look at the property that what is the relationship between lowercase kt plus 1 and the lowercase kt. It turned out that the lowercase kt plus 1 is defined as the aggregated k at t plus 1 divided by the level of the technology and the population at t plus 1. And then the kt plus 1 in fact equals 1 plus g multiplied by 1 plus n multiplied by the aggregated k. So then what we are going to have is that the uppercase kt plus 1 over et plus 1 and lt plus 1 is the definition for the lowercase t plus 1. And then the et plus 1 in fact equals 1 plus g et, and lt plus 1 equals 1 plus n multiplied by lt. So then what we turn out to have is that the 1 plus g and 1 plus n got cancelled out, and then what is left is the kt over et and lt. And that is exactly the definition of the lowercase kt. Therefore, we know that after we express the variables in terms of per effective worker, even though this model allows the population growth and the technological growth, but then if the economy is in the steady state, the lowercase kt plus 1 equal to the lowercase kt in the steady state. So then we can adopt this equation to help us pin down the steady state condition of this model.